Welcome to my talk on the nanoscale caterpillar, or how to achieve precise motion with random sticky feet. To begin with, I'd like to thank the people with whom I did this work: Gina Zhang, Fan Kui, Miranda Holmes-Serfon, and Dave Pine, who are all at NYU, where I am as well. I will start with a story that's probably familiar to each and every one of you, which is the story of your morning coffee. And every so often, we enjoy putting a spoonful of sugar into our coffee and stirring it with a spoon. Well, at the scales that I'm interested in, which are the nano to micro scales, there's no such thing as a nanoscale spoon. And most systems, whether they be biological or artificial, have to rely on alternative strategies to achieve complex functions, such as stirring, but not only stirring, also mixing, filtering, selecting, and so on. So for a while, I've been interested in finding alternative strategies to achieve these complex functions. Today, I'm going to focus on one of these ideas, which is to harness the nice and fascinating properties of sticky feet particles. So what are sticky feet particles? They're particles here that yellow circle that represents cells or colloids that diffuse around. And those particles are coated with a bunch of sticky feet that can selectively bind and unbind to other sticky feet on, for example, a surface. Those feet are also rather small, so they also diffuse around. Now, those typical particles, because they have generally a great number of feet, and that they are at small scales, I like to call them nano caterpillars. Now, such a very broad description of nano caterpillars actually represents a bunch of quite well-known examples, both in the biological realm and in the artificial realm. And I'm gonna give you two of these examples. One very famous example in the biological realm is viruses. Virus cells are typically coated with a bunch of sticky attachment points that attach to the mucus and then crawl, glide, and finally achieve the whole infection procedure. And here, understanding the dynamics of binding and unbinding of these specific feet is critical to understand how the biophysical process of infection is going to happen. Now that's for the biological realm, but also in the artificial realm, for a decade now, we've been able to synthesize large arrays of materials made of colloids that between themselves are attached via complementary DNA sequences that act as sticky feet. And for these systems that have interesting material properties, it's been shown that it's actually critical to understand how the particles move with respect to one another to achieve a very large scale, well-controlled crystallographic alignments of the particles. So here, once again, understanding relative motion is critical to scale up those materials. Now, in both of these examples, it's clear that what is interesting is to understand how those particles move with respect to one another. And this is what I aim to do, is to understand if we can control the nanocaterpillar motion. Now, it's a really hard question, and for several reasons. The first one is that when I think about those systems, they are very complex because they're very much temperature dependent. And then the second point is that these systems involve very different timescales and very different length scales. For example, the feet are really tiny in general compared to the length scales that the particles cover. So to answer that question of motion, I'm basically going to target the question and narrow it down to a kind of simpler question, which is the following. Well, these kinds of particles have different ways of moving. For example, one way is to skip. Skipping means detaching all feet diffusing around and then reattaching to the surface. Those particles can also slide. Sliding means you stay attached to the surface, but maybe you detach a point at the rear, reattach at the front, and this way, by and by, you're moving across the surface. Now, the question I'm going to answer here is to understand how fast is sliding over skipping and in which mode particles move preferentially. And to answer that question, I'm going to bring you through a kind of simplified theoretical model, but that can easily be built up and improved to account for more realistic systems. So what's the simple model? Well, the simple model is that of a particle. This spherical particle, now I'm going to consider is just some sort of rectangle that can move left or right, and it can only move left or right with a friction coefficient called gamma. Then that particle has one feet that can attach to the opposing surface. We're going to go to multiple feet later on. That feet attaches to the other feet with a rate of attachment Q on and a rate of detachment Q off. As I mentioned earlier, those feet are kind of small, so they diffuse around. And the friction coefficient associated with this diffusion is little gamma. Finally, those feet typically are like small polymers and have and act like springs. So I have in the parameters of the model a spring constant K attached to these systems. Okay, so for this simple system, I can write a set of stochastic equations that's describing what's going on, both in the unbound state and in the bound states, with rates of transitions from one to the other. Now, all of these equations in themselves are not telling me a lot of things of what are going on. Instead, what I do to have them tell me something is to use a very powerful mathematical tool called homogenization theory. That's kind of tedious, but that is very powerful. And that allows me to extract at long times that my particle is actually diffusing around with a diffusion coefficient that I will write here, d feet. And that writes as an Einstein relation kT over gamma feet, where gamma feet is the friction coefficient associated with all these attaching, detaching events. Now, what goes into gamma feet? Well, 1 over gamma feet writes P naught over gamma plus P1 over gamma plus gamma prime. Now, what do these terms mean? The first term corresponds to the unbound state. P naught is the probability to be unbound, and 1 over gamma is the inverse of the friction in the unbound state when the particle is not connected to anything. Now, in the bound state, I have this added contribution, P1 over gamma plus gamma prime. P1 corresponds to the probability to have one bond. And in the bound state, the friction coefficient is now gamma plus gamma prime. It's always greater than the base friction gamma. Gamma prime is positive. And gamma prime writes as a sum of over all these parameters that I've introduced earlier. I'm not going to go into the details of that, but the baseline is that actually the friction coefficient overall is just a nice weighted sum of the unbound and bound coefficients. Okay, so now by and by, I can improve that model to have 2 feet, 3 feet, and so on until n feet. And when I have n potential bonds, well, the expression for the friction coefficient overall, 1 over gamma feet, simply extends over all of the potential states, unbound, 1 bond, 2 bonds, etc., until n bonds. And in each case, it's weighted by the probability to have those n bonds over the friction coefficient when you have n bonds. And that friction coefficient simply scales like the number of bonds. Gamma n is roughly equal to gamma plus n times gamma prime. So I really personally like this mathematical expression because it's really simple in a way that it really tells something about what's going on overall and how to weight those different friction terms. But cutting the story short, what does this expression tell us about the initial question, which was, well, does my particle slide or does it skip? Well, everything is contained in this expression. When I look into the details of this expression, the first term corresponds to the unbound state. So it corresponds to skipping. So I can write a diffusion coefficient for skipping that writes KT P naught over gamma naught. And working out what's in this P naught and gamma naught, I find that it writes as KT over gamma times x to the power n, where x is a number smaller than 1, and n is the potential number of bonds. Okay, now what about sliding? Well, sliding corresponds to all the other terms because sliding happens when I have at least one bond. Okay, so summing up all those terms, I find that basically the most important term among all of these corresponds to the average number of bonds, n bar. And so I can write a diffusion coefficient for sliding that's typically KT P n bar over gamma n bar. P n bar is roughly equal to 1. And so that sums up to KT over gamma plus n, where n is the potential number of bonds, gamma prime 1 minus x, where x is my number smaller than 1. Okay, so that's mathematical expressions. Wrapping that all up, I find a diffusion coefficient for skipping, a diffusion coefficient for sliding, and both of them have a very different dependence in terms of the number of feet or potential bonds n. The diffusion coefficient for sliding scales is exponentially decreasing with the number of bonds, while the diffusion coefficient for sliding decreases as 1 over n. So as soon as I have just a few feet, it's gonna get much easier to slide than to skip. So the diffusion coefficient for sliding is gonna be much larger than that for skipping. So if you have lots of feet, you better slide than skip. So that's the mathematical result. But in the end, you can really summarize this into a very simple story, which is the following kind of take-home message. If I have just a few number of feet, well, it's going to be very easy to detach them, wriggle around, and then come back to the surface. So I'm basically going to be skipping like a grasshopper. But if I have a bunch more feet, it's simply going to be too hard to coordinate them all at the same time to skip. So I'm not going to skip, and instead, I'm going to slide on the surface and really move around like a nano caterpillar. So that's the theoretical story, but what's going on in the real world? And that's basically going to be the end of my talk. Well, in real systems, such as DNA-coded colloids, a lot of things are going on. So Fan Kui at NYU did a set of remarkable experiments using total internal reflection microscopy. And together with advanced modeling from my part, we've been able to identify what's going on at the interface between a DNA-coded colloid and a surface. And cutting a very, very long story short, we basically established that always potentially in contact are over than 500 sticky feet. So typically at the interface, there's more than 500 potential bonds that can be made. And this means that those kinds of systems are never going to skip. And most probably they're going to slide, or they're going to achieve more complex motion, but staying attached to the surface, such as rolling, for example. So that's the end of my talk. I hope that I've convinced you of the beauty of nanocaterpillars. They're really versatile systems that demonstrate a variety of different motion modes, and there's so much more to learn here. And most importantly, at the end of the day, I hope we'll be able to connect with biological systems such as cells and viruses and so on. And with that, I will stop and thank you for your attention. If you are staying around, well, I can tell you again the story of the nanocaterpillar and the grasshopper. Well, the nanocaterpillar wishes it could skip around, but it's just so hard to coordinate all of the feet that it has. And the grasshopper answers, well, skipping is definitely easier when you have just 4 feet like I have. And then the nano caterpillar wonders, oh yeah, but what about playing the guitar? So that's it. Thank you.